Los Angeles, 2 a.m. A Toyota Prius sits parked on a quiet street. Two figures slide underneath with a battery-powered angle grinder. 90 seconds later, they're gone. So is the catalytic converter. The owner won't discover the theft until morning, when their car starts sounding like a lawnmower. The damage, $1,500. The reason, a few grams of palladium, a metal more valuable than gold, platinum, or diamonds. Welcome to the world of palladium, the rarest and most valuable metal most people have never heard of. Every single car on the road contains it. Your smartphone has it. Medical equipment depends on it. And there's so little of it that total annual production worldwide wouldn't fill a standard shipping container. Today, we're going underground to see how America mines, processes, and refines this precious metal that's literally worth its weight in gold times 2. This is the story of palladium. Let's start with why you've probably never heard of palladium despite it being everywhere. The story begins in 1803 when English chemist William Hyde Wollaston discovered a strange silvery metal while refining platinum ore. He named it Palladium after the asteroid Pallas, recently discovered that same year. For over a century, palladium was a laboratory curiosity. Pretty, rare, interesting properties, but no real use. Then came 1970. American cities were choking on smog from automobile exhaust. Lead, carbon monoxide, nitrogen oxides. The air in Los Angeles was so bad that children couldn't play outside on bad days. The Clean Air Act forced automakers to drastically reduce emissions. Engineers needed a solution fast. They discovered that palladium, along with platinum and rhodium, could catalyze chemical reactions that convert toxic exhaust into harmless gases. The catalytic converter was born. And overnight, palladium became one of the most important industrial metals on Earth. Here's the problem. Palladium is incredibly rare. We're talking rarer than gold, rarer than platinum. Annual global production is only about 200 tons. To put that in perspective, gold production exceeds 3,000 tons per year. All the palladium ever mined in human history would fit in a single Olympic swimming pool. And here's the crazy part. 85% of palladium goes into catalytic converters. Every gasoline car manufactured contains between 2 to 7 grams of palladium. With over 80 million cars produced globally each year, demand is massive and growing. So where does palladium come from? Unlike gold or copper, you don't find palladium deposits just sitting around. Palladium occurs almost exclusively as a byproduct of nickel and copper mining. The largest deposits are in Russia's Norilsk region and South Africa's Bushveld Complex. But there's one place in the United States where palladium is the primary target: the Stillwater Mine in Montana. This is the only significant palladium mine in America, and it's where we're going underground. The Stillwater Complex sits beneath the Beartooth Mountains in south-central Montana. 2 billion years ago, molten rock pushed up from deep in the earth. As it cooled, dense metals like palladium and platinum concentrated in specific layers. The mine operates over 2,000 feet underground. Miners access the workings through a shaft that descends into solid rock. At the bottom, a network of tunnels extends for miles following the precious metal-bearing layer. Mining happens through a method called room and pillar. Miners drill blast holes in a pattern, load them with explosives, then retreat to a safe distance. The blast brings down tons of rock containing the palladium-bearing ore. Front-end loaders scoop it into haul trucks that carry it to the surface. Here's something most people don't realize. The ore is incredibly low grade. We're talking 2 to 10 grams of palladium per ton of rock. That means you need to mine and process 1 ton, 2,000 pounds, of solid rock to get less than 1/3 of an ounce of palladium. The economics only work because palladium trades at over $2,000 per ounce. The crushed ore travels to the processing facility where the real work begins. First stop, massive jaw crushers that reduce car-sized boulders into gravel. Then ball mills, enormous rotating drums filled with steel balls, grind the ore into powder finer than sand. Next comes flotation, a process that sounds simple but requires precise chemistry. Workers add specific chemicals to water containing the powdered ore. These chemicals attach to particles containing palladium and make them hydrophobic, meaning they repel water. Air bubbles blown through the mixture carry these particles to the surface, where they form a froth that gets skimmed off. The concentrated material still only contains a few percent palladium mixed with other metals. It goes to a smelter where temperatures exceeding 2,500 degrees Fahrenheit melt everything together. The molten mixture separates by density. Heavier metals sink to the bottom. Lighter impurities float to the top as slag that gets removed. What remains is still a mixture of palladium, platinum, rhodium, nickel, copper, and other metals. This material, worth thousands of dollars per pound, ships to specialized refineries for final processing. Refining palladium to 99.95% purity requires sophisticated chemistry. The mixed metals dissolve in strong acids, creating a complex solution. Through a series of precipitation steps using different chemicals at specific temperatures and pH levels, each metal separates out one by one. Palladium precipitates as ammonium chloropalladate, a brick-red compound. Workers filter it out, heat it in special furnaces, and pure palladium emerges as a spongy grey powder. This powder gets melted and cast into bars, pellets, or wire, depending on customer requirements. The purity matters enormously. Catalytic converter manufacturers need palladium at exactly 99.95% pure. Any less, and the catalyst doesn't work efficiently. Any more, and the cost skyrockets for no benefit. So, what makes palladium so special for catalytic converters? It has a unique property. At high temperatures, palladium catalyzes the oxidation of carbon monoxide and hydrocarbons into carbon dioxide and water. It also helps reduce nitrogen oxides back into nitrogen and oxygen. Inside a catalytic converter, exhaust gases pass over a ceramic honeycomb structure coated with palladium. The metal doesn't get consumed in the process. It just makes the chemical reactions happen thousands of times faster. One catalytic converter will process exhaust for the entire life of the vehicle without the palladium wearing out. And this is why thieves love them. That ceramic honeycomb contains 2 to 7 grams of palladium, worth $60 to $140. The entire converter sells for $300 to $1,500 on the black market. It takes 90 seconds to cut one out with a battery-powered saw. Catalytic converter theft became an epidemic in the United States starting around 2020. Insurance claims skyrocketed. Some cities reported hundreds of thefts per month. The pandemic amplified the problem when palladium prices hit record highs above $3,000 per ounce. But catalytic converters aren't palladium's only use. Electronics use it in capacitors found in smartphones and computers. Dentists use palladium alloys for crowns. Jewelers mix it with gold to create white gold. Chemical plants use palladium catalysts to manufacture pharmaceuticals and plastics. And here's something incredible. Palladium absorbs hydrogen like a sponge absorbs water. At room temperature, palladium can absorb up to 900 times its own volume in hydrogen gas. This property makes it valuable for hydrogen purification and fuel cell technology. The future of palladium is complicated. Electric vehicles don't need catalytic converters, threatening to reduce demand. But hydrogen fuel cells, which need palladium, could offset that decline. Industrial applications keep growing, and supply remains constrained by geology. The United States produces only 12 tons of palladium per year from Stillwater Mine. Russia produces 80 tons, South Africa 70 tons. These three countries control 90% of global supply, creating geopolitical risk. When Russia invaded Ukraine, prices spiked on supply concerns. Recycling offers a partial solution. About 30% of palladium supply now comes from recycling old catalytic converters, electronics, and industrial catalysts. That percentage will grow as prices remain high. From 2,000 feet underground in Montana to the catalytic converter in your car, palladium's journey is remarkable. A metal so rare that total annual production fits in a shipping container. So valuable that thieves risk arrest to steal it. So essential that modern life as we know it depends on it. Next time you start your car, remember, hidden in the exhaust system are a few grams of one of Earth's rarest and most valuable materials, quietly cleaning the air with every mile you drive. From ancient geology to modern technology, from Montana mountains to your car, this is Palladium. Thanks for watching. Hit that like button and subscribe for more incredible stories about the rare materials that power our modern world. See you next time.
Glass, it's in your windows, your phone, that beer bottle in your hand. But have you ever wondered how something so fragile starts as nothing more than sand? Today, we're going inside one of the most incredible manufacturing processes on Earth, where temperatures hotter than lava turn ordinary sand into the crystal-clear material that shapes our modern world. The story goes back over 4,000 years. Ancient Mesopotamians stumbled onto something amazing when they heated sand with certain minerals and got a transparent solid. But it was the Romans around 50 BC who really cracked the code with glassblowing. Then in 1608, English glassmaker George Ravenscroft changed everything by adding lead oxide to the mix, creating what we now call crystal glass. Today, the global glass industry produces over 130 million tons every single year, worth more than $160 billion. From smartphone screens to skyscraper windows, this ancient craft became absolutely essential to modern life. Let's head inside a modern glass factory and see how sand becomes glass. It starts in the batch house, where automated weighing systems measure each ingredient with precision down to 0.01% accuracy. The main ingredient is silica sand, about 70% of the recipe. Workers add 14% soda ash to drop the melting point, plus 10% limestone for stability. But here's the clever part. Most factories add up to 30% recycled glass to the batch. It melts at lower temperatures, cutting energy costs by 40%. Once precisely weighed, everything dumps into a specialized ribbon blender that ensures every particle is evenly distributed. Then it travels along sealed conveyor systems to the furnace. And this is where it gets intense. The furnace is an absolute beast, stretching over 120 feet long, 40 feet wide, and standing 3 stories tall. Inside, natural gas burners fire continuously at 2,800 degrees Fahrenheit, hot enough to melt steel. The flames switch sides every 20 minutes in what's called regenerative firing, where exhaust heat preheats incoming air, boosting efficiency up to 50%. Raw batch pours steadily in at 15 tons per hour. Over the next 16 to 24 hours, it slowly dissolves into molten glass. Workers monitor everything from a control room with over 50 thermocouples throughout the bath. Even a 10-degree deviation can ruin the entire batch. The molten glass gradually flows toward the conditioning zone, where temperature drops to exactly 2,400 degrees Fahrenheit, achieving perfect homogeneity. From here, different products take different paths. Let's follow flat glass first. For windows and car glass, the molten material feeds into a float bath, one of the most brilliant innovations of the 20th century. British engineer Sir Alistair Pilkington spent 7 years perfecting this process before its debut in 1959. And here's the genius behind it. Molten glass pours continuously onto a bath of molten tin, kept at exactly 1,050 degrees Fahrenheit. Glass naturally floats on tin because its density is only 2.5 grams per cubic centimeter, compared to tin's 7.3. As it spreads across the perfectly flat liquid metal surface, gravity and surface tension create glass with both surfaces perfectly smooth and parallel. The float bath stretches for nearly 200 feet. Modern lines control thickness by pulling at specific speeds. Pull faster, you get thinner glass down to 2 millimeters. Pull slower, you can create glass up to 25 millimeters thick. By the exit end, the glass is cooled to around 1,000 degrees and solidified enough to lift off without marking the surface. From the float bath, the ribbon enters the annealing layer, a temperature-controlled tunnel over 500 feet long. If you let glass cool naturally, thermal gradients would create internal stresses, making it weak and prone to spontaneous breakage. Instead, the layer cools it gradually over 2 to 4 hours. At the exit, automated cutting systems use diamond-tipped wheels to score the ribbon into massive sheets, often 10 feet by 12 feet or larger. But bottles and jars follow a completely different process. This is where the IS machine comes in, standing for Individual Section Machine. Invented in 1925, it's still the backbone of container glass production worldwide. Molten glass flows into a feeder bowl where rotating orifice rings cut the stream into precise portions called gobs. Each gob is sheared by pneumatic scissors with split-second timing, weights controlled to within 1 gram. A typical line has 10 or 12 individual sections, each making up to 4 containers simultaneously. Here's where it gets wild. In the blank mold, a metal plunger pushes down while compressed air at 40 psi blows up from below, forcing glass against the mold walls. This creates a parison, basically a thick-walled preform with the bottle's neck already shaped. Takes just 2 to 3 seconds. Then mechanical neck ring holders grip the parison, flip it upside down, and swing it to the blow mold in less than 1 second. Compressed air at 25 psi blasts through the neck, inflating it against the cooled mold walls. From molten gob to finished bottle in 8 to 12 seconds. A modern IS machine can produce up to 600 bottles per minute. Fresh bottles travel through an annealing layer for 30 to 45 minutes, cooling gradually. Then, every single bottle faces automated inspection. High-speed cameras check for cracks and defects. Infrared sensors detect stress patterns. Bottles must withstand at least 90 pounds per square inch internal pressure. Any failures get crushed and recycled back to the batch house. For specialty items like wine glasses, skilled craftsmen still use traditional glass blowing at glory holes, small openings into reheating furnaces. They gather molten glass on a blowpipe and shape it with hand tools. A master glassblower can create a wine glass in 5 to 7 minutes. Now let's talk about safety glass. Laminated safety glass in your car windshield starts with 2 sheets of float glass with a layer of polyvinyl butyryl plastic between them. The sandwich goes through rollers at 190 degrees, then enters an autoclave at 280 degrees and 175 psi for 90 minutes. This fuses everything permanently. The result? Glass that holds together when shattered. In an accident, broken pieces stick to the plastic instead of flying around the cabin. That's why windshields spiderweb instead of exploding. Tempered glass for side windows takes a different approach. Regular glass heats to 1200 degrees, then high-pressure air nozzles blast it from above and below. Surfaces cool rapidly while the interior stays hot, creating compression on surfaces and tension in the core. This makes it 4 to 5 times stronger than regular glass. When it breaks, it shatters into thousands of small cubes with dull edges instead of dangerous shards. Here's something mind-blowing. Gorilla Glass and other chemically strengthened glasses used in smartphones go through an ion exchange process. The glass is submerged in molten potassium salt at 750 degrees for 8 to 16 hours. Potassium ions migrate into the surface, replacing smaller sodium ions. Since potassium ions are 40% larger, they create a compression layer, making the glass incredibly scratch and impact resistant. Quality control combines automated systems with human expertise. For flat glass, laser scanners detect defects as small as 0.1 millimeters. Random samples undergo destructive testing. Chemical composition gets verified using X-ray fluorescence spectrometry. Everything must meet strict safety standards. The environmental impact has improved dramatically. Modern regenerative furnaces are 30 to 35% more energy efficient than those from the 1980s. And here's the crazy part. Glass is infinitely recyclable without quality loss. That beer bottle you recycle can become a new bottle, a window, or fiber insulation. Recycled glass melts at lower temperatures, reducing energy consumption by 40%. Some plants now run on 90 to 100% recycled glass. After manufacturing, flat glass often receives low-E coatings that reflect infrared heat while transmitting visible light, cutting heating and cooling costs by 30%. Container glass exits production lines at up to 1,000 bottles per minute, packed into boxes and stacked on pallets by robotic systems. The glass industry continues pushing boundaries. Researchers are developing ultra-thin flexible glass, less than 0.1 millimeters thick for foldable smartphones and rollable displays. New formulations create transparent materials strong enough for military applications while remaining optically clear. From ancient Mesopotamian workshops to cutting-edge research labs, glass has traveled an incredible journey. But at its core, the principle remains unchanged. Heat sand hot enough, add the right ingredients, and you create one of humanity's most versatile and enduring materials. So next time you look through a window, drink from a glass, or tap your phone screen, take a moment to appreciate the 4,000-year-old craft and modern precision engineering that made it possible. From sand to something extraordinary. Thanks for watching. Hit that like button and subscribe for more fascinating looks at how everyday things are made. See you next time. Picture this. A massive container ship longer than 3 football fields, weighing 50,000 tons, worth $200 million when it was built. Now it's worth more dead than alive. Every year, over 1,000 ocean-going ships reach the end of their life. And most of them end up on a beach in India, where an army of workers armed with nothing but cutting torches and sledgehammers tear these giants apart piece by piece. Today, we're going inside the world's largest ship graveyard, where some of America's retired naval vessels and cruise ships meet their final fate. This story begins in Alang, a stretch of beach in Gujarat, India. If you look at satellite images, you'll see something incredible. Dozens of massive ships lined up along the shore like beached whales. This 10-mile beach handles nearly 50% of the world's ship recycling. Over 400 ships per year, the scale is absolutely staggering. But here's the question. Why India? Why do ships from America, Europe, and Asia all end up on this particular beach? The answer changed the global shipping industry forever. Back in the 1970s, shipbreaking happened in developed countries like the United States and Britain. Dry docks, cranes, proper facilities, but it was expensive and slow. Then in 1983, a Kuwaiti tanker owner named Mohammed Hamza had a problem. His ship was too old to operate, but scrapping it conventionally would cost more than the steel was worth. He made a calculated decision: beach the ship at high tide in Alang, wait for low tide, and let Indian workers dismantle it. The labor was cheap, environmental regulations were minimal, and the beach's unique tidal range, reaching 40 feet, meant ships could be driven straight onto shore. It worked, and it changed everything. Today, Alang employs over 50,000 workers across nearly 200 ship-breaking yards. But before we get there, let's follow a ship's final journey. When a ship gets too old, usually after 25 to 30 years of service, operating costs skyrocket. Rust weakens the hull. Engines need constant repairs. Insurance rates climb. Eventually, shipping companies make the calculation: this vessel is worth more as scrap metal than as a working ship. The ship gets sold to a demolition company, often for $5 to $7 million, depending on size and steel prices. Cash buyers in India, Bangladesh, and Pakistan compete for these vessels. Then comes the final voyage, a slow journey toward the beach with a skeleton crew, sometimes just 10 to 15 people managing a ship that once required 50. As the ship approaches along, pilots come aboard. These specialists know the tides, the beach gradient, and the exact moment to drive the ship ashore. Timing is everything. At high tide, the captain opens the throttles one last time. The ship accelerates toward the beach at full speed, around 12 to 15 knots. The bow strikes sand. The momentum carries the vessel up the beach. As the tide recedes over the next 6 hours, the ship settles onto the sand, stranded. And this is where it gets wild. Hundreds of workers swarm the ship immediately. They have a tight window because the next high tide comes in 12 hours and they need to secure everything before then. First priority, drain all fluids. Fuel oil, lubricants, hydraulic fluid, anything valuable or hazardous gets pumped out into trucks. Then the real work begins. Workers climb aboard with oxyacetylene cutting torches, massive sledgehammers, and basic hand tools. No cranes, no heavy machinery, just human labor and fire. They start from the top, cutting the superstructure into manageable pieces. Each section of steel plate weighs hundreds or thousands of pounds. Workers use winches and chains to lower pieces down to the beach, where others cut them into smaller chunks. Here's something most people don't realize. Every single piece of that ship has value. The bridge electronics, radar equipment, and navigation systems get salvaged and sold. Brass fixtures, copper wiring, stainless steel railings. Workers systematically strip everything. The engine room is particularly valuable. Massive diesel engines weighing over 100 tons get dismantled piece by piece. These engines often get refurbished and sold to power plants or factories. Propeller shafts made from specialized steel alloys. Generators, pumps, compressors, nothing gets wasted. But the real prize is the steel hull. A large container ship contains 40 to 50,000 tons of steel plate. At current scrap prices around $400 per ton, that's $16 to $20 million worth of raw material. Workers cut the hull into sections roughly 10 feet by 20 feet, each weighing several tons. These plates get loaded onto trucks and transported to rolling mills across India, where they're melted down and reformed into rebar, structural beams, and new steel products. Here's the crazy part. The steel from one large ship provides enough raw material to build housing for a small town. Literally. That 50,000-ton vessel becomes rebar for apartment buildings, beams for factories, and steel for thousands of everyday products. The entire process takes 3 to 6 months depending on the ship's size. Container ships are relatively straightforward. Tankers are more complex because they carried crude oil or chemicals, requiring extensive cleaning before cutting can begin. Navy vessels sometimes contain hazardous materials like asbestos that demand special handling. Alang can handle anything. The largest ship ever broken there was the Nok Nevis, formerly the Yara Viking, the biggest ship ever built. Over 1,500 feet long, 657,000 tons fully loaded. It took workers over a year to completely dismantle. When they finished, there was nothing left but sand where a floating city once stood. But here's where the story gets complicated. Shipbreaking in places like Alang is incredibly dangerous work. Workers operate cutting torches while standing on steel plates. Toxic fumes from burning paint and coatings. The constant risk of sections collapsing unexpectedly. Fires break out regularly when cutting torches ignite residual fuel or gas. International organizations have criticized conditions at Asian shipbreaking yards for decades. The Basel Convention, an international treaty, restricts shipping hazardous waste to developing countries. Some argue end-of-life ships qualify as hazardous waste because they contain asbestos, heavy metals, and toxic coatings. This created controversy in the United States. When the Navy wanted to scrap old vessels, selling them to Asian breakers became politically sensitive. In 2006, the USS Forrestal, a famous aircraft carrier, sparked protests when the Navy sold it for 1 cent to a recycling company that planned to take it to India. The public outcry led to stricter rules. Now the U.S. government generally requires American military vessels to be scrapped in EPA-approved domestic facilities, even though it costs significantly more. But commercial vessels are different. When cruise lines retire ships like Carnival's older vessels or container ships operated by American companies, they often end up in Alang or Chittagong, Bangladesh, another major shipbreaking hub. The economic reality is stark. Breaking a ship in the United States costs $30 to $50 million because of labor rates, environmental compliance, and infrastructure needs. Selling it to an Indian breaker generates $5 to $10 million in revenue instead. That $70 to $80 million difference explains why most ships still head to Asian beaches. But change is coming. Modern facilities in India have started adopting better practices. Some yards now use cranes to lift sections, reducing manual labor, improved safety equipment, better waste management for hazardous materials. The Indian government, facing international pressure, has implemented stricter environmental standards. Ship owners must now provide detailed inventories of hazardous materials before a vessel can be accepted. Workers receive better safety training and equipment. Meanwhile, some developed countries are building modern ship recycling facilities that can compete. A facility in Texas breaks down offshore oil platforms and ships using advanced cutting equipment and strict environmental controls. European companies have opened high-tech yards in Turkey that combine Asian efficiency with Western safety standards. These facilities prove shipbreaking doesn't have to be dangerous, but they also cost significantly more to operate, and the economics still favor Asian yards for most vessel owners. The environmental benefits of ship recycling remain undeniable regardless of location. That 50,000-ton ship would sit as a rotting hulk somewhere, if not recycled. The steel gets a second life instead of requiring new iron ore mining and smelting, which consumes massive energy. Recycling one large ship saves the carbon emissions equivalent to taking 30,000 cars off the road for a year. The metals, electronics, and other materials reclaimed reduce demand for virgin resources. And for communities like Alang, the industry provides livelihoods for tens of thousands of families. Workers earn significantly more than agricultural labor in rural India. The scrap metal feeds India's massive steel industry, providing affordable building materials for construction projects across the country. It's a complex equation: economic opportunity versus worker safety versus environmental concerns versus resource conservation. Innovation continues pushing the industry forward. Some companies are experimenting with robotic cutting systems that can dismantle ships in enclosed facilities, capturing all waste and protecting workers from hazardous exposure. Underwater cutting robots for sections below the waterline. Others are developing mobile ship-breaking facilities, essentially floating dry docks that can break down vessels at sea and sort materials systematically before touching land. From military destroyers to luxury cruise ships, from container vessels to oil tankers, every ship eventually faces the same fate. Some end up in modern facilities with cranes and safety systems, but most still meet their end on a beach in India or Bangladesh, where workers with cutting torches transform floating giants into tomorrow's buildings. So next time you see a massive container ship passing by, remember, that vessel's journey doesn't end when it stops carrying cargo. Somewhere, eventually, it will drive itself onto a beach one last time, where an army of workers will transform it from a ship into the raw materials that build the future. From ocean giant to rebirth as steel. Thanks for watching. Hit that like button and subscribe for more incredible stories of how massive industries work behind the scenes. See you next time.